morning or good afternoon, everyone. My name is Alain Biem. I'm the Chief Data Science Officer for New York Life. And today I would like to discuss the importance of context in language model. So I will discuss this into three steps today. I will start by a quick overview about the nature of language model as we understand them today. And then I will follow that up with the quest of context representation within how we do NLP today, how we're going to do NLP in the future. And then some idea about how do we go from there. So if I start with what we mean today by a language model, this is a system that generates plausible human language. And so we have a variety of human language today. And so the challenge we're facing is how do we create a model that can effectively and efficiently leverage context so that we can deal with the intricacity and the variety we have into our human languages, right? And so that based on that, we can do a variety of tasks. You guys know well what are the type of tasks we're talking about here. So we need the language model to do language translations, translating a language from into, let's say, French into English or French into Japanese, doing speech recognitions, how to recognize human speech, sound, and how to understand what the sounds mean, the semantic understanding of those sounds, and how to do speech synthesis, basically how do you synthesize verbal word into something people understand. Text classifications, text summarizations, Q&A systems, some of those things that are hugely used today. But the cornerstone for this is basically a effectively and efficient language model that has to deal with the lexicon, the vocabulary that you have, the grammar that comes, the language that of interest to you, the syntactic view of this, and then the semantic view of that. So in short, basically, context is a key driver today for the usefulness of any language that we have. So based on that, then let me just quickly discuss the various level of language we have today, right? So when we look at the level of language, we start with the lexical level that we have. That has to deal with the phonetic, the phonology, and the morphology. Phonetic has to do with how language sound, the core sound we have into language. Certain language have more sound. Swedish, for example, have 16 vowels, right? And then Japanese are only 5 vowels. So it creates different type of sound per language. The morphology is basically how do you now form word together based on the sound that it does right now. And then when we move into that now, to the syntactic view of this, which is how to create sentences, how to create clauses, how to put things together, how to have the grammar that allow what word need to follow which word to make up a sentence. And then based on that, we can now move to the next level, which is the semantic view of the language. What is the meaning of the word, right? Regardless how those words are sound or represented, there is a meaning behind that. The whole point is to convey meaning, convey information when we use NLP today. And the semantic level deal with that aspect. Then we move by the use cases, the pragmatic cases. How do you use everything that we do right now? All of those levels, from the lexical level that deal with the phonetic, the morphology, the syntactic level deal with the sentence, the semantic with the meaning, and then the pragmatic with the use are quite relevant today. Now, context plays a role into that. As we move from the lexical viewpoint to the pragmatic viewpoint, more context is needed. You need to leverage context to do a better semantic understanding. You need to leverage context to do with the pragmatic of the language for that. Now, let's start with the lexical level, for example. Here I'm taking the example of a machine translation system. So in the old days, this is actually old, people start doing machine translation system. One of the early systems that was developed by IBM, working in collaboration with Georgetown University, they created the first machine translation system using purely lexicon vocabulary. That was done in 1954, a long time ago, before we have everything we do today. They were able to create a machine that can translate 16 Russian sentences into English, just using lexicon, right? So to do that, they need to have a dictionary, basically, a lookup word between the source language here, English, right? And then the translation from word to word let's say, from English to Russian, and then a synthetic viewpoint of that, how now you can now manipulate those words into a sentence to create a language. That was one of the early systems, and it is a purely symbolic representation and symbolic manipulation of information that you have right now. So that was the lexical viewpoint. Of course, as you can see here, there is no context involved. It's purely contextless. Now, when you move then to one layer, you move into the syntactic level of analysis. Now, language in that level is now seen as a sequence of words that carry a meaning for that. And so it's directed and dealt with by the grammar. The grammar basically is dictating how a word can follow another word for that. That gives rise to what we know today as computational linguistics. and basically using computer to better tackle, analyze what is that a law sequence, what is those rules that drive generating a particular language, be it right now. And so the key to approach and the true key philosophical view at the syntactic level of analysis is something we know as finite state grammar or automata, called FSMs into short, or context-free grammar, right? This is a Noam-Chomsky theorem of linguistics that was developed a long time ago. So I will expand more about these two aspects about before I move into the context. If I start here with the FSM view of the FSM approach for this, what now? So this is again part of the syntactic level of the language. Language here is viewed as a finite state machines or finite state automata, right? So an FSM is a mathematical model that describes a system with a limited set of states and transition between those states. Transition could be deterministic or probabilistic. There are many types of viewpoint for that. And you can use this machine effectively to basically represent a word. Basically, a word will simply be a sequence of letters of sound that word is made. Or you can use that to represent a sentence, and the sentence will simply be represented by the sequence of word, that is made up for that sentence. So it's a very powerful view to kind of having a broad use of applicability for that. So there's a whole world about that, about use of finite state machine. In the early way of speech recognitions, people use a hidden Markov model, and hidden Markov model is finite state machines. You have a set of state, you have transition between state, and they are probabilistic in nature. And it was a cornerstone of speech recognition for a long, long time before we moved today into the transformer-based technology. So what I'm saying is very powerful technology. It has had his time into representing language right now and is rooted into amazing body of work for that, and is used today into other areas, especially compiler system is still using finite state machine. The problem with finite state machine is that to represent language, especially human language, is going to have an expansive set of state. It's too big. You have to have a sort of a low path to work. And then how you represent those paths and how to connect those paths in your gram to represent language make it very hard, because you cannot cover all combination possible, right? It's hard right now. In this example, I'm showing a very example of a simple two-state machine, I and wish, two-state. And then that can generate many sentences. It can go to I wish, I wish, I wish, but it can never generate wish I, right? Because that part is not a law competitive, or it cannot generate wish I wish exactly, because right? So to be able to allow for all combination, it takes some time. That's why we move in the rise of context-free grammar was one way to solve that. You move one level up, you're now representing category of things. A sentence is just basically a rule. A rule. It can be a sentence is made of a noun phrase, which is in turn made of an article or a noun. And then you have many ways to have an article, right? You have many ways to have a noun. So you have that high-level view of context-free grammar as a generative grammatical rule to represent language, right? And so that was the powerful of context-free grammar, and then the key name for that was basically Chomsky theorem of context-free grammar. Now, Chomsky 1599, he made that very, very popular into that. And many people that have worked into computational linguistics, basically trying to parse languages, use context-free grammar is a very powerful technique. The problem, again, for human language is that it's very limited. Not all human language can be represented as a noun phrase, especially for certain language for now. And then the level of nuances you have into particular noun or pronunciation is also problematic. And the problem also is the change of meaning based on context. And that cannot be tackled effectively with context-free grammar. That's why we move into the probabilistic viewpoints of language models. A language now is a system that generate the most probable sequence of words based on some probabilistic measure. It makes things simple, right? Because it allows us now to use data-driven technique to represent language. Just represent the probability of the most probable word sequence you have based on the context you're dealing with, right? And that is exactly where we are today. And you can deal with a variety of contexts. You can have close context, nearby context, sentence-based context, domain-based context, or corpus-based context. All of those are basically various viewpoints about how you account for your contextual view in representing your language today. The rise of the probabilistic model for language. So I'll expand more on that because this is the era that we are today into language modeling. I start with simple, the n-gram representation. How to now account for the neighborhood of the word, right, to predict the next word. And so context here is basically the set of preceding word for a particular word. And there are a variety of techniques for doing this. I think typically you need to go through many assumptions for doing this. You need to do a markup assumption for now. You know, you can have, you know, one order, which is unigram, two order, which is bigram, three order, and now you even have more model today. I'm not sitting here. You have skipgram, which is now predicting the context itself out of one word that you have. Now, those probability can use different approach for probability. You can have a more frequentist view of things. You just count number of words in your corpus, or a bit more inferential view of things, which is now creating a model that can represent those probability. The key limitations that we currently made for that are the fact that typically if you use a sequence of words, this is the autoregressive viewpoint of things right now. The context is a bit unidirectional. It's just one way. Now you have technique today. We talk more about that are bidirectional with neural network that you can do. But the thing is basically that it's basically dependent on your corpus. When you have a low probability word, is a problem that you have to handle explicitly. And also depending on the corpus you have, different corpus will give you a different probability estimation. You need to deal with perplexity, which means somehow that accounting for a particular set of choice at one point in time based on the lexicon you have. And so some of those are some of the limitations that we're seeing today with n-gram model right now. And now, even if we move to a bit more complex model, like some of the model we're seeing today in using neural networks, for example, to better represent neighborhood, right? And then it's been very powerful because with neural networks, you can have a lot of data to handle, and you can have a very powerful probability estimation. So when you use neural networks, you have a set of work. The posterior of your prediction, basically the probability of having the next word based on the context, is basically a bit more close to what you want to do for your language model. So technique like recurrent neural networks, LSTM, GRU, have been used extensively for basically using neural networks to have a sequence of word moving forward. And the landmark paper from Benju in 2003, where he basically used a neural probabilistic model as a core language model, basically, which is integrated, create basically a lot of the innovation we have today, including things we see today as word embeddings, that we see, and I'll talk more about that. Now, the question that we typically have is, yes, this is good, you need large corpus, but the issue we sometimes have, it does not well capture the very good semantic similarity between words. We have issue with that, because remember, it's thread word by word, and the context basically based on the last 2, 3, 4 words, sometimes cannot capture the meaning of the whole context of the dialogue, because only look at the close neighborhood of the dialogue right now. And as all model, it can suffer from overfitting, right? And because of those problems, we've seen a lot of progress happening today with the rise of basically word embedding. How do you now basically represent word into a space that can also both capture the semantic meaning of the word as well as the syntactic meaning of the word right now? And so the rise of techniques like word2vec, FastDef, Glove we've seen today has created a landmark for what we see today. Embedding today is the core foundation for natural language processing, including language model. Why? Because by having a vectorial representation of the word, you allow numerical manipulations of a string that could not be done before. And by having that representation done well, you can both capture the semantic meaning of a word into a vectorial space and then the meaning of the word into the syntactic space, accounting for the lexicon that you have to deal with that. So it is basically a win situation into three levels: the lexical level, the syntactic level, and the semantic level. Now, between all of those models we have, WordVec, FastTech, Glove, all of those have pro and con, and some of those depending how the technique they use right now, right? So, some account for a broad contextual viewpoint, some into a very corpus viewpoint, and some have been used into many things. But one of the key drawback was basically that things like WordVec, FastTech, Glove, they could not account for various nuances into the semantic meaning. Sometimes language model can come up with many nuances. You can have the context representing that, but you have the tone, you have the different inclination. Sometimes it's very hard. And that's why when we move into using transformer technology, right, we move into context sensitive encoding, where you can have a word that have many small nuances, and you can have the same word having different type of embedding in the system based on different type of context. This is a powerful breakthrough. This is an amazing breakthrough. The fact that Transformer was able, and that was shown into early work on the vision, where Transformer can create something I call distillation of information. You start with raw, you go through many, many hierarchical level of informations, and then you lead basically at output. And that deep neural networks representations right now is just very powerful. And the fact that you add that to the attention mechanisms that allow you to go beyond local context, but global context, because now with self-attention and auto-attention, you can have basically knowing a particular sentence. It doesn't have to be in a neighborhood, it has to be very far. And that was a breakthrough where now you can have context be expanded, both local, both global, both within the sentence, both near to the word, into one single system that you can tackle. And by doing that, you can allow for different nuances of context sensitivity. Like you can be, you can make sure that the word bank here can mean a bank as a banking institution, or can mean a bank as close to the river. Same word, different meaning, different context. And some of those nuances could not be captured by early model, but with Transformer, we can do that effectively. And the work bank can have many representation, many different embedding in the system automatically. So Transformer gave rise to some of the breakthrough we've seen so far, things like, BERT, GPT-3, Palm, everything that we see today. Because of the influence of the Transformer, we can now have our disposal context-sensitive encoding available to us to use. So a word representation account for those nuances I discussed before, and those nuances can be driven from the sentence and from the corpus you have, and that can be expanded broadly. So based on that, based on Transformer, based on GenAI today, we are now moving into what I will call the rise of the dynamic context management. Today, into GenAI, your context is part of your prompt from your query. When you get your query, you can put your data into the query, you can put your tone, your persona in the query, you can put context of usage directly into the query. While the LLM that you use underneath is already based, it's been trained some internet corpus, it have the broad knowledge you need, but you can query something directly and you control the context directly by dynamic context management. And this is a new breakthrough we're having today with GenAI, where you can have context on the fly from query that you have. Your knowledge repository are refining context as you use it right now, and you can have a bit more richer dialogue. That is enabled by having all of those internal representation into the LLMs based on the transformer technology. But you, as a NASAD user, you can also create and constrain the constraint you have, right? Now, the limitation we're facing are that some of the things we know today into terms of hallucinations, right? And the fact that the autoregressive approach does not account for logical information explicitly, right? As we know, right, you still have problem with, we make progress on that, but basically LLM does not account for some of the information we have into some of those disparate information you have. And that's why we have hallucination today. So it's a problem. And we have had progress of that. Like the RAG technology today can be seen as a improved dynamic context management, right? Where you basically constrain your knowledge. That means your context of informations on your RAG technology. You have a set of document, you have a set of source document that you have, and then you use your embedding on those documents together with LLMs to kind of refine the context of application that you use into LLM query right now. Powerful technology. It has made some breakthrough. It had reduced the number of hallucination that we have today, and it has expanded the use of context, not simply from lexical to syntactic to semantic, but now to informational, to management at the high level right now. So that's where we are, basically, where we can now having a dynamic view of context that can be both domain specific, that can be both sentence specific, that can be based on the use query that we have. Now, the limitation is what I said, is basically that it's still based on the autoregressive view of NLP that we have today, basically by predicting the next word based on the context right now. But doing that meantime is very powerful, but how do we account for fact? How do we account for reality? And that is where the next thing is going to be. How do we go from there? Accounting for the fact that the model we have today, the language model we have today, does not account for the world they live in. We don't know reality as it is, right? And so when we complement our language model with a system that accounts for reality and fact, can we create a system that accounts for the physical law of nature, economic, socioeconomic models, put them together into a repository of analysis, maybe a part of our broader context of usage, world context, where do we live in? What is the reality we live in? What is the socioeconomic we live in? We expand the use of context beyond simply the query we have, but the world we live in, the reality we live in right now. So a world model has a broad context of applications that include law of physics, socioeconomic model, everything that we know, and that driving our LLM approach, right? Driving the context query we have as my assessment about where we go from here. Okay. So thank you all for listening, and I appreciate you for more. Hopefully, I'll be going to be able to answer some questions either today or at some point, some other mediums. I appreciate you for listening. Thank you again. Thank you. Bye.